Hi, welcome back. In this lecture, I would like to talk about our last quantum computing primitive called quantum phase estimation. This is an introduction to the quantum phase estimation, and I want to focus on the concepts of eigenstates and eigenphases of QPU instruction or QPU gates. In some sense, the quantum phase estimation is similar to the amplitude amplification and the QFT quantum computing primitives. Phases estimation extract tangible, readable information from superposition. And what we're going to extract by using the phase estimation quantum computing primitive are the eigenphases of an eigenstate of a particular QPU instruction. So differently from the amplitude amplification and QFT primitives, phase estimation teaches us an attribute of an operation acting on a QPU register, rather than an attribute of the QPU register state itself. So it's really about having a quantum computing operation that is expressed by a gate, and then find the so-called eigenphase that is characteristics of that particular quantum computing gate. So let's start focusing on one particular gate that at this point we know quite well, that is the Hadamard gate. So we know that Hadamard gate is our gate to the superposition of state. If we start from state 0 or state 1, applying the quantum computing Hadamard gate, we obtain a superposition of equal state. Right. So the only difference when we start from the first for state 1 is that we see a flip in the phase. So let's consider the Hadamard gate action on two special input states that are shown on these slides. You see here we have the probability of reading the 0 state, that is 85.35%, and then the probability of observing the state 1 after the observation of 14.64%. An interesting part, when we apply the Hadamard gate on this particular state, superposition of states, we obtain the very same superposition of states. So you still observe here 85 and 14% observing state 0 and state 1. We have a similar situation if we have a probability of observing the state is 0 of 14% and conversely the probability of observing the state 1 of 85%. We apply the Hadamard gate. We obtain same state in terms of magnitude of the state. So you see the area of the circle are actually the same. What you observe though is actually a global flip of the phase by 180. So this it goes up, right, by 108, and then this goes down by 108. So the phase, the global phase, is impacted by 180 degree. So we just flip it, the global phase, but the magnitude remains the same. So we saw that in these two particular cases, applying the Hadamard gate, the amplitude remains the same. And the second case, we have a global phase flip of 108. So the application of the Hadamard gate to these two states leaves the second state, the state unchanged. So these states impervious to a certain QPU operation, in the sense that if you apply that, these states we got the same state. So these states are impervious to the operation except for the global phase, and these states are called operation eigenstates. It turns out that every QPU operation has a distinct and unique set of such special states, for which it will only impact an important global phase. Let's look again the eigenstate for the Hadamard gate. The global phase acquired by a particular eigenstate is called the eigenstate eigenphase. In the case of the first eigenstate, we have an eigenphase of 0, because applying the Hadamard gate to this particular state, we obtain the same states, so that we don't observe any change of the global phase. And this means that the global phase is 0 and the eigenphase is 0. In the second case, where we observe a flip of the global phase of 180 degree, in this case the eigenphase is going to be 180. To summarize, these are the two eigenstates of the Hadamard gate, because if we apply the Hadamard gate, we obtain the same state in terms of magnitude. However, for the second eigenstate, we saw a flip of 180, and that means the eigenphase is 180. In the case of the first one, there is no flip, so the eigenphase is equal to. It's important to note that the eigenphase and eigenstates of an operator are unique. So the particular eigenstates and associated eigenphases that I've been discussing in the previous slides are specific to the Hadamard gate. That also means that other QPU operations will have entirely different eigenstates and eigenphases. So if we change the gate, we will have different eigenstates and eigenphases. The eigenstates and the eigenphases of a QPU operation determine the operation uniquely because no other QPU operation has the same set of eigenstates and eigenphases. So what is the phase estimation quantum computing primitive that does? Well, the phase estimation will help us determining the eigenphase and eigenphases associated with the eigenstates of a QPU operation. So we'll take our QPU operation and then applying the phase estimation, we give as input the eigenstates, and we will determine the eigenphases associated with the eigenstates. In particular, the output of this quantum computing primitive will be a superposition of all the eigenphases. The basic intuitive mechanism of how phase estimation works is that we have some Q operation called the U, which acts on n qubits and has some set of eigenstates, which we refer as U1, U2, and Uj. Using phase estimation, we want to learn the eigenphases associated with each of the eigenstates. So we will give it as an input eigenstates or a superposition of eigenstates, and when we will obtain as results a superposition of eigenphases. It's important to note that the eigenphase associated with the jade eigenstates is always a global phase. It's not a relative. We saw, for instance, in the previous slides that the relative phase does not change, but the global phase will be impacted. So we can specify by the angle theta j through which the global phase rotates in the register state. So to summarize, given a QPU operation U and one of its eigenstate Uj, the phase estimation quantum computing primitive returns some precision the corresponding eigenphase angle theta j. This is the last slides of this lecture, and talk to you soon.